In this video, we are going to be taking a look at 3.4 out of reach, finding lengths. That's not what I wanted to do. Okay, there we go. Finding lengths with similar triangles. That's what we're going to be looking at today, and triangles are going to be nestled inside each other. But before we do this, let's go ahead and review the idea of ratios and proportions. So if you remember, I know you've learned about ratios in the past, you've talked about ratios in the past, so go ahead and try to write your best definition of what you remember a ratio being, and then we're going to talk about a definition, how closely it is to you. Hopefully you get an idea of what it is, but go ahead and write what you think a ratio is. Okay, so a ratio is essentially a comparison of values, usually in the form of A over B. Like a ratio, probably the most common way that you would see it, price per gallon, right? If you think about gas, when I was 16, I remember buying gas for 87 cents per gallon. It seems like forever ago. But nowadays, it's upwards to around $2, $3, $4, depending on the week, really, per gallon. So that's a ratio. You're comparing how much money do I pay per 1 gallon. Miles per hour, that's another ratio. It's a comparison of two values, miles and hours. Gallons and dollars, or dollars and gallons. Okay, so that's what a ratio is, usually in the form of a fraction. Now let's take a look at a proportion. Go ahead and think about what you think a proportion is and write down your definition. I'm sure you've heard it previously in the past. It has to do with ratios, but what do you think a proportion is? Now, proportions are two equivalent ratios that are set equal to each other. And you've done this without really even thinking that you're working with proportions, but I know for a fact that you've worked with proportions. For example, let's start with equivalent fractions. Okay. Now, a fraction, it can be seen as a ratio. It's a comparison of numbers, 1 to 2. That's a ratio. That's also a fraction. Okay, let's think about how would I find an equivalent fraction? Well, if I wanted to find an equivalent fraction, I would multiply both the denominator and the numerator by the same value. So 1 times 3 is 3, 2 times 3 is 6. So 1/2 and 3/6 are equivalent fractions. And in fact, I could go ahead and find other equivalent fractions as well. So let's say I wanted to take 3/6 and multiply both the numerator and the denominator by 4. That gives me 12/24. So all of these are equivalent fractions. Now, remember what a proportion is when two equivalent fractions are set equal to each other. So if we set two of these fractions set equal to each other, so let's take these. 1/2 is equal to 12/24. That's a proportion, okay? Now, what we're going to start getting into is the idea that, hey, sometimes we don't know all the parts of this proportions or this puzzle. So let's say you don't know what this bottom number is, right? That's a big question mark. But you can use the idea that these are equivalent ratios to figure out what that number is. Meaning, how do I go from 1 to 12? What is my factor? What is my scale factor? There's that word coming back again, right? I multiply by 12, which makes sense because if you think about what we did up here, right? We multiply by 3, then 4, 3, then 4. 3 times 4 gives us 12. So if I multiplied 1 by 12 to get to 12, I also need to multiply the denominator by 12, and then that gives me my unknown, which is 24. Okay, we're able to take proportions and solve for unknown values, which is where we're going with all of this. So make sure all of this is in your notes and that it makes sense to you in some way. Highlight it because we're going to continue to come back to these big ideas of ratios and proportions and how they work. Now that we have a review of ratios and proportions, let's get back into 3.4 out of reach. So let's understand the story that we are being told here. Darrell, Angie, and Tanya are designing a triangular boardwalk that crosses a river. They make several measurements and sketch the diagram below. So this is your lab sheet. If you look at lab sheet 1, or whatever lab sheet this is, lab sheet 3.4, okay? This would have this diagram. You can look at it there or look at it in the book. It's entirely up to you. The students use similar triangles. That's very important. Similar triangles. We've been talking about similar triangles to find distances that are difficult to measure. For example, the distance across the river would be extremely difficult to measure. No fun. So the diagram shows a specific type of similar triangles. These are called nested triangles. Write that in your notes. Nested triangles. They are triangles that share a common angle. In other words, nested triangles, what you have to understand, that they are similar. They share a common angle and they are similar to each other. For example, in this problem right here, we have two triangles. We have our big outer triangle, which I'll draw right here. Okay, and this is assumed to be in the right angle. Then you have this other triangle because you have this river flowing through, and then you have this other triangle down here. I'll do that one in green. So this green one, this is our nested triangle. Okay, and you notice they share common angles. So right here is the angle that they share. Right there, that's your shared angle. Okay, and so these triangles are similar to each other. So what I like to do is I like to pull out that nested triangle. So for example, I'm going to take that nested triangle and I'm going to pull it out so that I can see that I have this triangle here and the other triangle. So I have this triangle and now this triangle. Those are similar triangles. And that's how I'm going to approach solving this problem. I'm going to pull that nested triangle out so I can see two separate but similar triangles to solve. Okay? Now, we're going to look at figuring out what that distance across the way is. So on A, the triangles in the diagram on the previous page are similar. We already talked about that. What is the distance across? Right? So go ahead and try that on your own. See if you can't figure out what is the scale factor from the little one to the big one or the big one to the little one, depending on how you want to do it. What is the scale factor? How do I find some of those missing sides? And then how do I use that information to find the distance across? Go ahead and try part A on your own and then come back to the video. And if it's easier, you're welcome to use this lab sheet. Okay, so if we look at this is how I set it up. And you are welcome to set it up however you want. But again, I pulled this nestled triangle right here. I pulled that out, and that's what I have right there. Okay, so I have that nestled triangle separate so I can see it's separate, but it's still similar to that larger triangle. And I labeled things that I knew, right? So they gave us the measurements. That is 80 right there. This is 120 right there. And this is 140. Now, obviously, it's not perfect to scale, but it gives me a visual representation of what I'm looking at. Then below, I went up and now I'm trying to figure out my scale factor. So if I look at corresponding sides, okay, so corresponding sides are two sides of triangles that should be similar. For example, this side and that side should be similar to each other. So I'm going to set up a scale factor by setting up a ratio of corresponding sides. So we're doing, right here, we're doing a ratio of corresponding sides. Okay, now that's going to be, let's do big triangle to little triangle because this will give me, what do I need to do to go from little to big? All right, so that'll be 140 over 80. Which will simplify down to 14 over 8 or 7 over 4. Okay, so this is my scale factor. Okay, if you write that as a decimal, so I'm going to write it over here, scale factor. So I have more room. It's 7/4, which is 1.75 as a decimal. That means that the big triangle, this is a triangle, is 175% larger than a little triangle. Okay, write that in your notes. Write all of this. How do we figure out our scale factor? What is the ratio of corresponding sides? Remember, we defined the ratio, and by setting up the ratio of corresponding sides, we found our scale factor, which is 7/4 or 1.75. And what does that sound like when we think of how much bigger is the big triangle? It's 175% or 1.75 times the size. Okay, now, all of that help us to solve this problem, because what we really want to know, I'll highlight in purple, is this distance right here. That's what we want to know. Okay, so it's going to be something like this distance there. Well, we have to figure out what is this total distance here. Okay, and we don't know that yet, but we can use the scale factor. Well, if the scale factor is 1.75, and we know the corresponding side for that particular side is 120, these two are corresponding. So if I take 120 times 1.75, that should give me that new length, which is 210. Now, don't be quick to answer the question or try to think that that's the answer, right? It's just saying that, hey, now this side is 210. So that's from stake 3 all the way to tree 1. That's what we found. But we don't want that, okay? So now we need to figure out, given that this is 120, what's this purple length? Well, it's easy. We just take 210 minus 120. Oops, that's feet. Minus 120, and then that gives us 90 feet. Okay, so it is 90 feet across the river. That is that purple section that we're trying to find. Oh, purple. There it is. That's that purple section that we're trying to find there. Okay, so you should have gotten 90 feet on that first one. There's lots of different ways. This is the most thorough. Make sure this makes sense in your notes to you when you go back and look at it. Go ahead and try to answer part B. Think back to what we said about perimeters. If we know the scale factor from side to side, for in this case is 1.75, what does that tell us about the perimeter? Go ahead and try to answer that question and pause the video and then come back. All right. The perimeter always changes at the same rate that the given scale factor tells you to change. So in this case, the perimeter, right? So it changes by 1.75 scale factor, or scale factor of 1.75. So the perimeter of the bigger triangle is going to be 175% larger than the perimeter of the smaller, just like the side lengths. Perimeter and side lengths, they're going to change at the same rate. Area, however, is going to change by 1.75 squared, whatever that is. I don't even know what that is. I'd have to punch that into a calculator. But perimeter changes at the same rate the scale factor changes. And looking at C, the diagram on the previous page shows 3 stakes and 2 trees. In what order do you think Darrell, Angie, and Tanya located the key points and measured the segments and angles? Explain your reasoning. So we're thinking, okay, how did they measure these out? What order would make sense to do these? So go ahead and kind of write out how you, if you had to approach this problem, what order would you put those stakes in? And measurement. So you still have to measure between trees. Okay. So on this one, so what wouldn't make sense Okay, this would be an example of a wrong answer, one that would not make sense, that if you actually did this, people would laugh at you and be like, what in the world were you thinking? You put no forethought into the final job, like what you needed to do, all of the steps in between. Okay, so that's if you went from tree 1 to stake 1, stake 1 to stake 2, stake 2 to tree 2, tree 2 to stake 3. Okay, that would make no sense. You're crossing the river twice. So whatever method, number 1, makes you walk the least, and then cross the river only one time, that's the method you're going to want to do. All right. The only thing I would say is, hey, you might want to cross the river here because there's some rocks. Those are either rocks or hippos. But hey, if they're hippos, it'll be a great swim. And on the last one, this is the other part of your lap sheet. The bottom part of your lap sheet, you have this diagram right here. Another group of students sketches a different diagram with similar triangles. They put their stakes in different places. Use the diagram below. Does the second group get the same measurement? So what do you think? We're going to see if we can get the same measurements or if they get a different measurements. We're still trying to figure out what is this distance across the river. So we're still trying to find that distance. So go ahead and do what we did for the first one, but now they have different measurements. See if you still get 90 or if they get something different. Okay, so the first thing I'm going to do is I'm going to pull out my triangles. So I have my big triangle. Oops, let me make it a little nicer here. So I have my big triangle that I'm going to pull out. Okay, and it's 140 across. I don't know what this measurement is right here. That's one of them I'm going to try to find. But the one that I really need to find is this one that goes across the river. Because then I have that other triangle in there, and I'm going to pull it out as a separate triangle. I know that this is 30 feet. This is 35 feet. So let's figure out what my scale factor is. In order to do that, I need to figure out what my ratio is. Okay, so my ratio, I'm going to do big triangle to little triangle. Okay, and I need to find corresponding sides. And my two corresponding sides are here and here. And then my other two corresponding sides are going to be here and here. All right, but I know 140 and 35. I know those side lengths, so it makes more sense to use those. So 140 to 35. And if you divide those, you get 4/1. And this is your scale factor. All right, meaning we took and multiplied all those sides times 4. So we're going to need to do the same thing. So we're going to need to take 30 times 4 as well. And now that question mark right here turns into, oops, I wanted this. That question mark turns into 120. Because we now know what that is. The 30 times 4 is 120. Okay, now we have enough to answer the question. We have all the pieces. We just need to put them together, right? So we know if we take 120 minus 30, that will give us this purple section right there. And what do you know? 90 feet. Okay, so yes, they are the same. Okay, they are in fact the same. You get the same answer regardless. That's the great thing about math, right? Whether one of those was right or wrong, as long as you measure correctly and follow the properties, you'll be just fine. And that'll do it for 3.5, Out of Reach. Thanks for listening.